atoms breaking apart. No longer could the atom be considered the smallest particle in nature. Evidently, the atom was not an indestructible little ball after all. But then, what was it? The first clue to this question came from Lord Ernest Rutherford of England. The year was 1911.
Today, I used the fast-flying fragments of radium as tools to probe into the atom. I placed a small sample of radium inside a solid lead block. The lead absorbed all the rays except those that were allowed to escape through a small opening in the block. One might say it was a sort of atomic gun. To make the ray bullets visible, I used a fluorescent screen. For a target, I chose a very thin leaf of gold. But to my surprise, the bullets from my atomic gun passed right through the gold leaf as though it wasn't there. It was like shooting at a ghost. This was truly amazing because the gold leaf was a solid wall, 2,000 atoms thick. So the atom can't be as solid as we always thought. Then, unexpectedly, one out of thousands of bullets ricocheted, striking something solid. I can only conclude, then, the atom is mostly empty space, like a cloud or shell. But occasionally I hit something solid. It must be very small, a tiny particle in the center. I shall call it the nucleus of the atom.
With Rutherford's discovery of the nucleus, scientists began to understand how nature builds her atoms. The shell of the atom appears solid, just as a fast-whirling fan seems solid. Actually, the shell is composed of a whirling swarm of tiny electrical particles called electrons. They circle around the nucleus like planets around the sun. So the atom is like a tiny solar system. But scientists are ever curious. Like the fishermen who examined the vessel he had hauled ashore, they began to probe the atomic nucleus for its secrets. They found that it was composed of small particles electrically charged. They called them protons, which means primary particles. Later, to the great surprise of science, other strange particles were discovered in the nucleus. They had no electrical charge. They were neutral, and so they were called neutrons. At last, the mystery of the atom structure was solved. How amazing nature is. Think of it. There are countless solar systems of atomic suns and planets in everything. There's a whole universe in the tip of a pencil. Even in this tiny pencil dot, there are billions of times more atoms than there are people on our Earth. There are many kinds of atoms. It's interesting to see how they differ in the various elements. It's a fascinating study in numbers. Let's start with number 1. The simplest atom in nature. 1 proton and 1 electron give us the element hydrogen, a very light gas. Nature always keeps an electrical balance in her atoms. So, if the nucleus has 2 protons, it will also have 2 circling electrons. This makes an atom of helium. There are also neutrons in the nucleus that add to its weight. And so, by simple addition, nature builds the atoms of all her elements. 6 protons and 6 electrons and some neutrons for carbon. "16 and 16 for sulfur. "26 iron. "47 silver. "79 gold. "92 uranium, the famous radioactive element. Here, nature has crowded so many protons and neutrons into the nucleus that it becomes unstable. Finally, it throws out a small fragment, and in this way, radioactive rays are born. These rays cannot be seen, heard, or felt. The Geiger counter is used to detect their presence. It gives off audible clicks when the rays pass through it. And there is another instrument which even makes the rays visible to the naked eye. This special device is called a cloud chamber. It contains a tiny bit of radium which gives off a constant shower of atomic fragments. Of course, the fragments themselves are much too small to be seen, but you can now see their trails. Each new vapor trail shows that another atom has thrown off a fragment. Each atom does this only once in its entire life, but there are so many atoms that this activity is going on almost endlessly. We might say that a radioactive atom is like a set mousetrap. Both contain energy. The traps on this table represent the atoms in a piece of radium. Every so often, one breaks down all by itself, releasing a bit of energy. But radium is useless as a power source. There aren't enough atoms releasing their energy at the same time. But nature knows all the secrets of the atom. Since the beginning of time, she has used atomic energy to power the whole universe and to light the fires in the sky. The best example is our own sun. These are actual time-lapse pictures of the sun's rim. That vast display of energy comes from an atomic fire raging deep in the core of the sun. If this was an ordinary fire, the sun would burn to a dead heap of ashes within a few thousand years. But so much energy is produced by these atoms that the sun will go on shining for billions of years to come. For a long time, nature alone knew how to open the vessel that contained this mighty force. To man, however, the vessel remained closed. Finally, he discovered the secret of how to open the vessel himself. The fisherman used his knife, and man too found a tool that broke the seal. The year was 1938. The place, Berlin, Germany. The leading character, that strange metal called uranium. Again, it turned out to be the star of a sensational scientific discovery. Otto Hahn and Fritz Strassmann were probing the secrets of the uranium atom. Like Rutherford, they used atomic bullets. They used neutrons, the neutral particles that were discovered hidden in the nucleus of the atom. The neutron is an ideal bullet. Since it is neutral, it isn't deflected by the electrical charge of the atoms and flies through them in a straight course. Finally, it struck a nucleus. The uranium nucleus split in two. Atomic fission had been accomplished. But this wasn't all that happened. Two neutrons were released from the split nucleus. One bullet was used to split the atom, and two new ones were created in the process. Now we have two neutrons to split two atoms. This implied a fabulous prospect, a nuclear chain reaction in uranium. Let's go back to our mousetrap atoms. We can create a chain reaction with them. We'll use our two ping pong balls for neutrons. They will be released when the atom splits. Now all these mousetraps are the atoms that will be in the game. They are set, loaded, and ready to go. To start the chain reaction, all we need is one neutron. It has to trigger just one trap. The ping pong balls that are released will set off two other traps. And then we'll have four balls flying to trigger more traps. I think you can see what is going to happen. Watch. An atomic chain reaction works in exactly the same way. One neutron is enough to start it.